up first, we have Samantha Hasler, who is a PhD student at MIT, who's going to be telling us about their algorithm for reducing detection confusion in directly imaged multi-planet systems. So take it away, Samantha. And
All
just a
right.
heads up, I will turn my camera back on when you have 2 minutes left.
Okay. Thank you so much, Eric. All right, everyone. So yeah, I'm going to tell you today about our deconfuser. So just to get started, I do like to give a little bit of context when I talk about this tool. And if you saw me give a talk at AAS, you've already heard all of this, so you can maybe tune out for a minute. But essentially, the deconfuser was designed with future direct imaging missions such as Roman, the ELTs, and the Habitable Worlds Observatory in mind. So these missions will enable the direct detection and characterization of planets orbiting closer into sun-like stars. So on this slide here, you're seeing a simulated system. This is from the HABEX final report. And this would be a 3-planet system around a sun-like star imaged at 4 different times. So these systems are going to be more complicated to observe and interpret because there will likely be more planets per image. The planets might have relatively short orbital periods, and we might also have false or null detections while we're observing. So all of these factors contribute to a confusion problem that has been predicted for future observations. Now, this confusion problem arises when multiple planets are detected around a star over several observation epochs, and we don't know which detection belongs to which planet. So on this slide, you're seeing an example simulated system with 2 planets. Here we have 3 images essentially stacked on top of one another in the left panel. And the issue here is there are 2 different ways to fit the orbits to these observations. The first set here in the middle, you can see gives a fairly coplanar system with low eccentricities. The second set on the right-hand side, you can see the system is no longer coplanar, and they also have higher eccentricities and are slightly closer together. So the issue is both of these do provide equally good fits to the data, which means we need to consider some other methods to decide which set of orbits really fits the system. So the deconfuser was developed to address and perform an assessment of this confusion problem. It can fit orbits to detections of planets, given their astrometry, and this does result in many possible combinations of orbits. So we still need to decide which detections belong to which planet, which is the deconfusion step. The fast nature and design of the deconfuser allows for Monte Carlo studies of confusion rates as a function of various parameters. So this includes the system parameters, like the viewing angle, the observatory parameters, like the inner working angle, or the number and spacing of the observations. And these Monte Carlo studies allow us to then draw some conclusions about how well we can deconfuse systems and what our observation strategies need to be to keep confusion rates low. So this brings me to walking through the steps of the deconfuser, which again was designed to address the confusion issue. I do want to emphasize on this slide that the deconfuser itself is highlighted with this red box, and then the kind of inputs that go into the deconfuser are on the outside, on the left, and what we can get out of it are on the right, that confusion rate analysis. So the first thing the deconfuser does is accepts unlabeled astrometric measurements of planet detections. Here is an example of simulated planet detections. This would be 4 detections of an image, again, all stacked on top of one another. And the observations here you can see have been equally spread over nearly a 2-year time span, so the different shapes correspond to different times of detection. The second step in the deconfuser performs the actual orbit fitting step by performing a 3D parameter search. The deconfuser assumes Keplerian orbits, which are defined by 6 parameters. However, each detection, when we're observing a system, only provides 2 constraints, and that's the 2D location of the planet in the image plane. Therefore, any 2 detections could be fit with infinitely many Keplerian orbits. So rather than solving the inverse problem of fitting orbits to a set of points in 2D at given times, we search over a 3D parameter space of semi-major axis and the x and y vectors of eccentricity in the plane of the orbit. Now, the deconfuser does this for several reasons, one of them being that a search over the full 6D space of orbital parameters is computationally taxing. So the other 3 orbital elements are fit implicitly, and those are the 3D rotation angles that transfer the orbit from the image plane into 3D. And then if you're interested in knowing even greater detail about the orbit fitting routine, I do encourage you to take a look at the deconfuser paper, which gets into a lot of the nitty-gritty details. So the next task for the deconfuser is to try to fit orbits to all combinations of unlabeled detections and assign or partition the detections by orbits that fit them well. The deconfuser fits by the fewest points first and increases their number only if the fit is good, and that's to avoid fitting orbits to all possible point combinations. Then the deconfuser iterates over all partitions of detections, or which groups of detections belong to which planet. Orbits that have more matches are ranked higher, and groups of detections with higher ranking orbits are returned first. However, sometimes this ranking alone is not sufficient to deconfuse observations, so we do need to perform some ranking refinement and tie breaking. The final step in the deconfuser would be to rank orbits and partitions based on factors other than the number of matched candidates. So this could include astrometry errors, consistency with planetary phase curves, priors on distributions of orbital parameters, or an almost never-ending list there. So the extra criteria then would allow for a more refined ranking scheme to break ties between orbits that are otherwise ranked equally. For example, orbit matches with a smaller number of matched planets would have to be ranked higher if their planetary phases or maybe their orbital parameters were more statistically likely. So this step is part of our currently in progress work to update that ranking scheme within the deconfuser. So that brings me to talk a little bit about our current and future work. Our current work, and then my personal focus with the deconfuser, has been to add considerations for planetary illumination phase to the ranking portion of the tool. And that's because when we're observing a system that has higher system inclination, we do expect to see a change in planetary brightness throughout a planet's orbit. So we can try to fit orbits a little bit better by accounting for the changes in brightness. There are also many avenues to pursue with future work, which include accounting for priors on orbital parameter distributions. We could also examine whether accounting for dynamical stability of systems has an effect on confusion rates, as well as any null or missed detections while we're observing, astrometry errors, or false detections. And finally, we could maybe take a look at how planetary color could improve orbit fitting or otherwise affect confusion rates. So this is a workshop about sharing our tools with each other, so I do want to mention how you can apply the deconfuser to your own work. I think the first point is probably fairly obvious based on the talk, and that's that you could use the deconfuser to perform your own confusion rate studies. So maybe you have some systems in mind or parameters you want to explore. You can go ahead and take the deconfuser and do your own work there. But the second point that's also pretty exciting is you can take the deconfuser and apply it to real ground-based data. So we have done a little bit of kind of a proposal early study with this, but it is possible that there could be additional planets hiding among the speckles in an image. So close to that inner working angle, you see a lot of potential point sources. So you can use the deconfuser to sift for low signal to noise candidates near the inner working angle. What you're seeing on this slide are high contrast images from the Gemini Planet Imager Exoplanet survey. This is the system HD 206893. And then we have a confirmed planet marked with a white arrow here and some potential point sources marked with orange arrows. So unlike speckles, planets will change their location in an image over time in a way that's consistent with the laws of orbital motion. So what we can do is discard points that don't appear to match any orbit around the star. So here we've gone ahead and taken those pictures and used the deconfuser on some of those potential point sources. On the bottom row, we have example groups of points that can be fitted with an orbit with an eccentricity below 0.3 and a maximum astrometry error of 0.5 AU. So in this case, only one of the matched orbits has a similar inclination to the confirmed planet in the system, but this is just to illustrate how the deconfuser would be applicable for your own work. So that brings me to my summary here. I think the main points are that we have this awesome deconfuser tool that can be applied in your work. It quickly fits orbits to detections of planets in 2D images, and it's great at deciding which assignment of detection to planet fits the data best. I personally think it would be really awesome to see other people take the deconfuser and apply it to some current ground-based data and search for those low signal planets that might be closer to their stars. And then if you're interested, we have performed a Monte Carlo study with the deconfuser, and that you can see a little bit more about in the paper linked on the bottom QR code here. But it does show that the deconfuser is successful in eliminating confusion with 4 observations, except for systems that are highly inclined. And with that, I did describe the current and future work. So on the top, if you're interested in taking a look at the code, there's the link to the GitHub. And again, the paper is linked on the bottom. So I'm happy to take any questions.
All right, thank you very much, Samantha. So we have plenty of time for questions. If anyone has any, feel free to raise your hand or post them in the discuss talks.
There's one in the chat.
Yes, okay. We have a question from Andreas Quierenbach in the chat. To guide intuition, it would be interesting to know how many observations are needed to deconfuse the Galilean moons. Is something like that difficult because of the inner working angle and the edge-on geometry?
Yeah, so I'm maybe not sure if I fully understood the question. I don't know if they're here to unmute. Um, the paper does go into a little bit more detail about how many observations are needed based on the system inclination. But essentially, for systems that are less inclined, I believe 3 observations is good enough to fit orbits in most cases. The deconfuser does start to struggle with those highly inclined systems, which is one of the reasons that we really wanted to add the planetary phase illumination in, because we think that can help out quite a bit when we're looking at those changes in brightness.
Yeah, I was wondering how many observations did Galilei have to make until he knew there were 4 moons and got their orbits right?
Oh, that's a good question. I don't know that off the top of my head. I don't know if anyone else might.
I don't either. I know he made quite a lot of observations. It's funny, he actually made so many that I saw a paper once that actually used the timings of his observations to get a ridiculously long baseline for understanding the orbital evolution of the systems. But I don't know how many he actually needed just to come to his initial conclusions.